My name is Maxwell, and this is my lab 4 on oscillation. The purpose of this lab was to examine the motion of a mass oscillating vertically on a spring and understand and predict oscillating motion using fundamental principles. In this lab, we compared the predictive motion with observed data using Python and Tracker and plotted the energy changes occurring in the system for the predictive motion. A preview of this lab, the observed tracker model and the predictive Python model share similarities in the x and y direction, and the change in the total energy is in fact 0. The key concepts for this lab are below, one of them being Newton's second law, which is F net equals delta P over delta T, which is related to the velocity update formula below and the position update formula below. The energy principle is an also very important concept in this lab. Which is the change in energy of a system equals the work done on the system plus the exchange of thermal energy between the system and the surroundings. You can see this written in the equations below. Other energies that are also available in this lab is the kinetic energy plus the gravitational potential energy plus the spring potential energy. There are also possibilities of other energies in the system. As you see to the right, you can see a free body diagram of the experiment. And we also learned that with the energy principle, the change in energy in this specific experiment is 0. In Tracker, we know that the system is the Earth, spring, and the mass, and there are no surroundings. If the system is set to include all the elements that do work on the system, then W star equals 0 and Q equals 0. This is how the energy was 0 in the previous slide. The video frames per second is 0.095 frames per second. The object mass from the pre-lecture video was 4.02 kilograms. The start time was 0. The initial position is as follows, and the initial velocity is 0. The final time, or the amount of time this video ran, is 9.947 seconds. As you see to the left, there is the graph of where the center of mass of the object is in the x and y direction, and to the right of that graph we have a picture of the starting point of where the mass is. Here are the initial conditions written with the Python code. As you can see, there is the mass and the initial position vector. We have the gravity is 9.8, the spring potential, or the spring constant from this pre-lecture video is 6.83, and the relaxed length of the spring is 1.123. We specified the vector L, and then we also specified each equation that was from 2 previous slides ago of the kinetic and the gravitational potential energy and the spring potential energy, and then total energy equals 0. This next slide shows the computational loop, which includes the time, which is the final time of my data, and then a update formula. We have the position and velocity update formula plus F net, where we iterated through that. With the change in energy and time graph, as the change in the spring potential energy increases, the change in the gravitational potential energy decreases accordingly. Both lines are crossing the axis around the same time. The position and time graphs, while both graphs show a strong resemblance to the actual and predicted data, the predicted data is more accurate regarding the actual data in the x direction. Some potential errors that could have occurred are the excluding of other sources of energy, such as thermal or rotational or electrical, other sources of non-accounted for friction, such as air resistance, and other errors regarding the placement of the data point where trying to track the center of mass. Here are the discussion questions. Is the energy principle satisfied? According to the graph yielded from the Python code, the energy principle is satisfied at any given point on the graph. If the energies were summed, the total energy would be 0. The oscillation between the change in the gravitational energy and the spring potential energy is the easiest way to see how the energy principle operates. With any increase in the potential energy, there is a decrease in spring potential energy. Here are the estimations of the oscillation periods. The average oscillation period in the x position is 1.519 seconds. The average oscillation period in the y direction is 1.633 seconds. This difference is 0.0 0.303 seconds. This difference between oscillations has an impact on the spring force, the spring potential energy, and the calculation of the spring constant. This difference can be caused by drag and create tracking of the center of mass in other human era. Thank you for watching.